I'd like to talk about how special right triangles can help us find exact trigonometric function values for angles of 30, 45, and 60 degrees. First, let me say these are kind of special. An exact value means that I can express the trigonometric ratio, the trigonometric function value, without any rounding. That's not something we can do for most angles. If I find, for example, the sine of 25 degrees, we'll get some decimal expression from the calculator, but there's no real nice way for 25 degrees. There's no very nice way to express that exactly without any rounding, without any approximation. So 30, 60, and 45 degrees are kind of special, and the reason why is because they relate to special right triangles. So let me explain the situation here. Suppose we have an equilateral triangle. An equilateral triangle has three angles of 60 degrees each. All the angles are the same, and because they have to add up to 180, if we divide 180 by 3, we get 60. So 60 appears in this special geometric figure. If I divide that into a pair of right triangles, because of the symmetry involved here, the angle up at the peak gets split into a pair of angles, and each of those is 30 degrees. And so we get a special right triangle drawn on its side, just because, I don't know. Drawn on its side, we get a special right triangle with a 30-degree angle, a 60-degree angle, and a 90-degree angle. And what makes this special is that we know, because this is an equilateral triangle, I know that all three side lengths are the same. And so for convenience, let me say that the side lengths are all 2. When I drew that vertical line, when I dropped the altitude to the other side, it split that opposite side exactly in half, because of the symmetry. And so that means that in this other diagram, the side opposite the 30-degree angle, I can think of that as length 1, and the side opposite the 90-degree angle, I can think of that as having a length 2. In any case, I know that this side length is going to be exactly half that side length. The third side length, of course, we can find from the Pythagorean theorem, a squared plus b squared equals c squared. The hypotenuse is 2, and one of the sides is 1. So squaring that, I get 1 squared is 1. B squared, let's say, is unknown. And the hypotenuse squared is 2. I can solve for b. B squared has to equal 3, and b equals the square root of 3. So the side opposite the 60 degrees is the square root of 3, which means, for example, the sine of 30 degrees, I can take this triangle to find the sine of 30 degrees. Opposite 30 degrees, I have a 1. The hypotenuse is a 2. And so the opposite side over the hypotenuse is 1/2. The cosine of 30 degrees, well, adjacent to 30 degrees is the square root of 3, and the hypotenuse is 2, so I have the square root of 3 over 2. So these are exact expressions for those trigonometric ratios, something that we weren't able to find for, say, a 25-degree angle. In a similar way, from this triangle, we can find sine of 60 degrees, we can find cosine of 60 degrees, and because we know the three side lengths of the triangle, we can really find any trigonometric ratio for a 30-degree or a 60-degree angle. For 45 degrees, to evaluate expressions involving 45 degrees, we can use the fact that a right angle with 45 degrees in one corner has to have 45 degrees in the other corner. So if one of the acute angles is 45 degrees, so is the other. Because together they have to be 90 degrees, and so if one is 45, so is the other. Well, that means this is an isosceles triangle. So if this side length, let's say, is 1, then so is that side length. Again, using the Pythagorean theorem, we can determine that the hypotenuse in this setup would be the square root of 2. So to find some trig ratios, let's say, sine of 45, we're interested in knowing what that is. Sine of 45 degrees, well, it's the opposite side, which is 1, divided by the hypotenuse, the square root of 2. So this would be one way to express the exact ratio for sine of 45. We could rationalize the denominator. If I multiply the top and the bottom by the square root of 2, I get the square root of 2 over 2. The tangent, to look at another ratio, the tangent of 45 degrees, well, that's the opposite over the adjacent side. They're both equal to 1 in our diagram, and for any 45, 45, 90, they would have to both equal the same thing. And so the tangent of 45 degrees equals 1. I encourage you to take a few minutes and try to find the other trigonometric ratios for 30, 60, and 45 degrees using these two special right triangles. I hope you enjoyed the video. Thanks.